Okay, I'm very pleased to introduce our speaker today. Is Brian Ade from Oak Ridge. Brian is an R&D staff researcher within the Nuclear Energy and Fuel Cycle Division, specializing in reactor physics analysis. He's currently leading the core design and analysis for the Transformational Challenge Reactor program at Oak Ridge. So he has a very cool job in a very cool project. The TCR is utilizing additive manufacturing for critical core components, and through this aims to provide a revolutionary platform to dramatically reduce deployment costs and timelines for nuclear energy systems. So, once again, very pleased to introduce Brian, and look forward to your talk, Brian.
Great, thanks. Thanks for having me. It's a pleasure to be here virtually. I'd love to be there in person to give the talk, but obviously, maybe in another year or so we can do similar things in person. But virtual will be the way it goes for now. So, as Ben said, I am leading core design for the Transformational Challenge Reactor, and what that really means is my primary job is related to reactor physics, making sure that the reactor is going to operate properly, it responds properly under transient scenarios, and so on and so forth. There's lots of other things that go along with that. The actual design of physical components, a lot of times nuclear engineers, especially in the R&D world, don't get into designing many physicals. Most things are paper reactors, and TCR from the start has been somewhere in between a paper reactor and a real reactor. So just a little bit before we get started about facilities that we have at Oak Ridge National Lab. There's the main lab space, and then just in the last couple of years, Oak Ridge has taken occupancy of another building that is called the Manufacturing Demonstration Facility, or MDF for short. This is really an excellent facility to take a tour of if you're ever in Oak Ridge and know someone that has access there. It's really amazing the type of research and R&D that's going on there. This is far bigger than just nuclear, so it applies to lots of different areas. But this is where all of our additive manufacturing and other advanced manufacturing techniques are taking place at the lab. So this is really where additive is centered. We also have other advanced manufacturing technologies there. So I am, if I were actually on site, I would spend half my time between the main campus of the lab and half my time at the manufacturing demonstration facility, where our people that do the CAD modeling and people that understand 3D printing more than I do reside, so I can work closely with them. But wonderful, beautiful new facility that houses all these different 3D printing technologies, where we're doing R&D on these technologies, all the way from very small printing, very fine detail things to printing large scale components in metal and concrete as well. So that's a little bit about the facilities that we get to utilize as part of the TCR program. Quick outline for the talk. I'll just go over a few slides of TCR program overview, and then I want to go through just a couple of slides quickly about the overall design of the TCR, the current design of the TCR system. And the reason I want to go through that is to help you understand how quickly we've gone from assessing a number of different concepts to a real reactor design that we think could be built in a short time frame. And then after that, I'm going to go through some specific examples of how we're leveraging advanced and other additive manufacturing techniques to gain performance increases or better performance in other areas related to the reactor performance. Okay, so TCR is really organized into four major thrust areas. Design for additive manufacturing, that's where I reside. So we are constantly thinking about, really I had trouble with this to start with in the TCR program. You have to kind of rethink how you design reactors, because additive manufacturing allows you to do things that you wouldn't otherwise do, or that you don't typically see in traditional nuclear reactors. So there are some limitations to what you can, but there aren't many. So you can do lots of cool and interesting things. To go along with those advanced new designs, we have advanced high-performance materials that we've developed. And really, the materials that we've developed for the Transformational Challenge Reactor, I think, are going to have far-reaching impacts throughout the nuclear industry in the years to come. And they are the key technologies that really enable a very small reactor design that uses not very much high-enriched LEU and would be able to be deployed in a quick timeline. We are working also toward embedding sensors in some elements in the TCR fuel elements, TCR fuel stack, I guess I'll say, to monitor temperature and stress and strain and things like that. And then the fourth major component is, and really this is really transformational R&D, which is essentially data analysis that you get as part of the additive manufacturing process. Because part of the main part, one of the big parts of additive manufacturing is you're laying down material piece by piece rather than casting it or milling it away or so on and so forth. So because you're laying it down piece by piece, essentially melting metal together, you get a great amount of detail on how that part was constructed, and then you can start to use that detail combined with new data analysis algorithms to essentially redesign parts or increase the performance of parts that you print. Okay, so let's talk a little bit about what we call our agile design approach. This is a term that is taken directly from software development, but it really works well. Really works well for design as well. So we organize major areas that we need to accomplish, major sticking points. We organize those into thrusts, get the not thrusts, but sprints, get the right people in the room, and then have those people work on that for a significant amount of time. 2 weeks to a month is what a typical sprint is, and then solve a problem. Now, in terms of design, what we do, as I said before, I sit closely with our CAD designers and in the same facility where all of our 3D printing is going on. So the first thing we do is we come up with a design concept, and we run a number of simulations to make sure that design concept is going to meet various design criteria like system size, power level, so on and so forth. As soon as we have an actual design in a CAD model, we immediately go to try to print some of those parts. So in parallel, we're still doing analysis, design and analysis, continuing to iterate within the design, but we're also starting to manufacture actual parts that are related to that design. During that manufacturing process, we're monitoring the manufacturing to essentially try to detect any defects. And then we test and analyze those parts after they're done to very quickly determine what changes we need to make in those parts to make them perform at a higher level. And so, those four thrusts and this agile design process is really driving toward breaking this 40-year hiatus in building a new non-light water reactor, advanced reactor in the U.S. So we want to leverage these technologies, and we believe we can leverage these technologies to deploy a new system in a reasonable budget and a short timeline. Okay, so that's kind of the high-level vision of TCR, and now we'll get down into more details of the actual TCR design and the process we use to do design. Okay. So here are the overall design requirements that we started with really about 2 years, really honestly a year and a half ago. So everything you're seeing now in terms of design was done in about a year and a half. So so we really want to leverage these scientific advancements that have been made over the last 10 to 20 years that previous reactor designers did not have access to. We're not going to try to operate a reactor for a long period of time, and the reason that is because we have a number of material issues, compatibility issues, irradiation stability, things like that we're not going to be able to test in the time frame to deploy a new system. So we're relying on a relatively short operation to get around some of those hurdles. We're going to explore complex configurations that really are enabled by additive manufacturing. And really, neutronic and thermofluidic design optimization is the focus here. We'd like to be able to operate at temperatures higher than light water reactors to gain some greater amount of efficiency. The design activity should span about 2 years and support deployment in 2023. So this is kind of this is the previous vision. We're moving a little bit on the vision now, which I can answer a few questions related to later. But right now, we're unlikely to get the amount of funding we need to deploy a system in 2023, so we're expecting that timeline to be pushed out a little bit. We're going to collect data from these embedded sensors that we're working toward. And the high level is there's really no specific design or application that was targeted. We took a wide view of what our capabilities are, what our strengths are, and then tried to design a system that made sense given the size constraints of the system, the HALU constraints of the system, and the power level that we needed to get out of the system. So here are some of those constraints. The core needs to fit in an envelope of 1 square meter. It needs to be deployed in an existing facility. We don't really have time to build a new facility, so it needs to go somewhere at the Oak Ridge site or somewhere else in an existing building. And the timeline, of course, drives some of these constraints. And another additional major constraint is we're using HALU, so that's 20% enriched uranium. We need to use less than 250 kilograms of it. So that's really not a whole lot. We kind of applied that constraint to ourselves because we know that if we're only operating for a short amount of time, we should be responsible with the material that we're given and not request a whole lot of it. Okay, so this is summer 2019. So this is, as I said, a year and a half ago, we had 4 different reactor concepts that we were looking at, 2 thermal and 2 fast spectrum concepts. The fast spectrum concepts are the ones on the right. Thermal spectrum concepts are the one on the left. The thermal spectrum concepts both have a yttrium hydride moderating material. Fast spectrum systems use the same technology, but they do not have the yttrium hydride moderating material. So there's one, if you look along this, the top row, both of these reactor types use TRISO embedded in silicon carbide as the fuel, and you actually can build a fast reactor with that system. Now, you don't see any cooling channels in the fast system here because we're assuming the channels are homogenized. Again, the models you see in these pictures are relatively rough models, unrefined models, because we're doing very fast design iteration to determine whether these systems are going to work. Okay, so we did a lot of analysis on these. There's a conference paper from Pfizer 2020 that looked at these different design options. And so what you see here is very quickly the fast concepts require more fuel than what we're going to be given. Either of the UO2 in stainless steel or the TRISO and silicon carbide concepts get us below that 250 kilogram requirement. So now we down selected and started doing additional analysis on these 2 systems. Okay, here's what these 2 systems, the fuel of these 2 systems essentially looks like. The top is the TRISO and silicon carbide. The TRISO is traditionally manufactured TRISO fuel particles. They get poured into an additively manufactured shell, which is what you see there on the right. Now, the complex cooling channels that you see there on the right are just an illustration of the art of possible. They're not necessarily optimized for performance, but it starts to expand your imagination into what you could do with this type of technology. The picture here on the left, upper left, is an actual surrogate fuel element that is completed using this process, and it's essentially one of these Y-shaped kind of fuel elements that you see in the model plots here on the right or on the left. On the bottom right, you'll see pictures of UO2 and stainless steel concept. And so the far right picture was for the fast reactor concept. That's essentially a hexagonal fuel block. This can is additively manufactured. What you see on the inside there springs. We don't want to have to mill uranium dioxide after it's been sintered. So essentially what we said is, well, can we just put this into a fuel can? Well, you don't get very good contact if you just put that into some cladding. So what we decided to do was additively manufacture spring features on the outside of that to enhance heat conduction. So you can essentially just push a green fuel form down into that and then weld a cap on top of it. And then there's an annulus around the outside where coolant flows. Same concept here on the bottom left, but it's this same Y-shaped coolant channel that you see here. Okay, so those are the two concepts that we got started with. The down selection between these two concepts really informed by parallel manufacturing and modeling and simulation sprints. So we started to try to manufacture a blowdown test for this type of concept. So this piece you see on the top right is actually additive manufacturing as it's going on. So we're additively manufacturing this flange that goes on the top of this barrel. This whole thing on the top right was additively manufactured. We also printed a full-scale prototype to see what that would look like. And then we eventually did a blowdown test to understand how much frictional loss and things like that we would get out of this type of system. We were doing most of the down selection came from modeling and simulation, indicating that the UO2 and stainless steel was unlikely to be able to operate at the power levels that we wanted, whereas the TRISO and silicon carbide concept those power levels with margin to spare. So that's essentially the design option that we took. Further on down the road, we decided these Y-shaped fuel elements, there's a lot of them. So let's combine 6 of those into this cog-shaped geometry. So we have the Y shape here on the bottom left, and then with the arrow pointing to the right, we get to this cog-shaped fuel element that has internal cooling channels. The green you see is yttrium hydride cylindrical moderating rods. Okay, so that's kind of the design concept that is the current status of the TCR. We did a lot of analysis to get to that point and change the shape of those channels, and we're still doing analysis and optimization on this underlying concept now. And there's some real advantages to this this layout that we have here that I can get into eventually. So essentially, we progressed very rapidly using lots of modeling and simulation and lots of people doing additive manufacturing and informing us what we'd be able to print and manufacture on a short timeline. Okay, so really, we very quickly, the other thing that was going on at the same time is we weren't for sure that we could construct this yttrium hydride moderator form. So we stood up a major thrust to develop that moderator form. And in the end, we very quickly were able to make large pieces of solid yttrium hydride that are currently being irradiated. And steel encapsulation of that material matured the most rapidly, so that's what we're using in terms of current design. So yttrium hydride is a very special moderator. It's similar to zirc hydride. The nice thing about yttrium hydride is it's stable to higher temperatures than zirconium hydride. Only hydrogenous moderators at a core size of less than a meter are going to give you a critical reactor. Basically, any other moderators, you're going to need a larger envelope. So that's what we're choosing between zirc hydride and yttrium hydride, which is the plot you see there on the left. So here's the TRISO fuel form as it stands right now. We print a shell, which is what you see there on the left. That is printed using a technology called binder jet, which is essentially we use silicon carbide powder. A binder jet is kind of like an inkjet printer. It lays down a very fine layer of glue, and then we spread another layer of powder, and then the next layer, we add another layer of glue, and then a layer of powder, layer of glue, layer of powder, until we build an entire part. So you can have very fine dimensional control with this. The part, when it comes out, is not ready for full use. It has to go through an additional process called chemical vapor infiltration to essentially make that shell more solid. After that shell is more solid, then all we do is pour in TRISO particles. After the TRISO particles, after the fuel element has been filled, we then fill that element with silicon carbide powder, and shake that down, do a vibrational process to essentially fill in all the spaces with very fine silicon carbide powder. And then that goes through another chemical vapor infiltration process. And after that, after a couple days in that CVI furnace, the fuel element comes out, what you see on the right. On the right is a fully assembled mini TCR fuel assembly. So there's 4 fuel blocks stacked up, and there's a yttrium hydride rod in the middle, and then this handling mechanism up on top. That top block that you see is a true TRISO-filled, it's surrogate TRISO, but a TRISO-filled fuel block. Okay. So hopefully these videos work. The thing we can do as part of this is we can, after these parts are built, we can take a look at those using the advanced characterization techniques that are housed at the manufacturing demonstration facility. I'll play this video so you guys can see the type of data that we get out of this. This is an X-ray tomography scan, and so this is part of the stuff that I'm involved with. It's essentially scanning the part, getting every TRISO particle location, and then constructing an as-built model, as constructed model of all those TRISO particles, and understanding how it changes the power distribution when you really model those particles, and how it changes the thermomechanical behavior as well. So that's the end of the video. Hopefully it came through okay. We'll see some more about this later on in the talk. Okay, high-level design overview. I'm going to skip through these relatively quickly because we want to get to the interesting stuff, which is the additive manufacturing stuff. I don't want to waste too much time discussing kind of these high-level design details. One cool thing that we developed was this magnetically controlled shutdown rod. There's a magnetic solenoid up top, and I'll play the video here so you can see how this works. So essentially, there's nothing touching the rod from the inside. This is completely externally controlled. It's an externally controlled shutdown rod because we did not want to develop or try to go down the path of developing high-performance, high-pressure seals so that control rods can move in and out of the pressure boundary of the reactor. So essentially what you're seeing there is everything inside that tube would be pressurized. And we don't have to have any seals or anything like that. So that's just the shutdown rod. The control system would be external to the reactor. Here's the layout of the system. The layout is those fuel elements that I told you about before. Each fuel element has a yttrium hydride rod that runs down the middle. That's essentially serving 2 purposes: moderation of neutrons, and it ties all of the fuel elements together into a single stack. And then the yellow rods you see here on the right, the yellow circles, those are what we call free yttrium hydride rods, and those would be inserted in kind of one by one, and that's what we're going to use, or that's what we would use to flex the reactivity of the system, is the free yttrium hydride rods, the amount of moderator that we include in the system. Okay, so you're always going to have some moderator in there because you have to have that in the internal rods, and that's essentially the tie rod, but the other free rods are free for us to optimize in terms of reducing power peaking and getting the excess reactivity of the system correct. So here's how one of those fuel elements go together. I've already explained this in other slides, so we'll skip over this one and come back to it if there's more questions. So this is some of the design details here. These cups on the left, far left-hand side of the picture, these are additively manufactured stainless steel. That's what the fuel elements fit down into, and the free yttrium hydride rods fit down into. And then we also have additively manufactured top alignment plate that keeps all those yttrium hydride rods and fuel rods in proper alignment during operation. Okay, so now what I want to talk about is being able to leverage these technological advancements for better nuclear design. So you've gotten now a high-level overview TCR, and now we're going to go into some specific examples of how we're using advanced and in particular additive manufacturing to enhance our design of the system. Okay, so this is leveraging neutronic design for leveraging additive manufacturing for neutronic design. So what you're seeing here is on the left-hand side of the picture, you're seeing we call the power factor, the peaking factor of the reactor. So that's essentially the power of each fuel element divided by the average power. And the baseline design you see up there in the very top right. So the maximum peaking factor is between 1.55 and 1.6. So almost 1.6. So the high power element is 1.6 times the average. And what we want to do is we want to be able to reduce that peaking factor to some lower amount without affecting the excess reactivity. So what you want to do is reduce the power peaking, but not reduce how long you could potentially operate a system. So what you can do with additive manufacturing is very easily essentially reduce the amount of fuel that's in each of these fuel elements. So the outside dimension of the fuel elements, the fuel cogs, all stay the same. And then we start to modify the thickness of the outer shell, the outer skin of the fuel cog, going from 1 millimeter up to 2 millimeters, and doing some amount of design iteration and optimization based on that wall thickness. And what you see here is you can optimize the wall thickness and reduce the peaking factor down to 1.5 with very little. Even lower than that, down to 1.45 or 1.4, without a really significant impact on excess reactivity. So that's a very positive outcome. This is something that would be very easy to implement. So this is really very simple changes in the additive manufacturing process. Just print a thicker wall to reduce fuel where you're having higher peaking. So very, very simple approach to take, and one that would be easy to do. There's much more complex design optimization that you can do in neutronics, but up to now we haven't had time to do that because we've been mostly focusing on deployment of a system and not optimization or detailed optimization of a system. What you can also see there, the points are colored by how much uranium you have in the system. So that's how many kilograms are in the system. So you see in the current design, we're well less than 250 kilograms, and we can use quite a bit less than that if we optimize a little bit and not have a significant impact on excess reactivity. Okay. So the second part is really thermofluidic optimization. So this is looking at internal cooling channels. So in this particular iteration of the fuel element design, we have cylindrical fuel channels, and what you're seeing here is kind of the baseline case, which is the top left, which is just straight, smooth cooling channels that run through the middle of the fuel element. Top right, you see a sinusoidal wavy surface. This is designed to increase pressure drop, but also increase the convective heat transfer. So we're using this metric called thermal performance factor to essentially increase the thermal performance, or try to increase the thermal performance of these surfaces. These are all surfaces that you could easily additively manufacture into the design. The bottom are some different airfoil turning vanes. So these are small. I'm not for sure if these would actually survive additive manufacturing or not. Periodic ribbed surfaces would definitely survive. These would be pretty easy to print as well, and could provide you with a significant increase in performance. Now these are easy. We did this modeling and simulation in Star CCM. We printed some of these cases, but we ended up doing additional optimization. We decided, well, there's no reason to have cylindrical cooling channels anymore. So why don't we look at cooling channels that are different shapes and different sizes? So now we have the baseline design here is again those cylindrical cooling channels in the top left, because we could additively manufacture any shape that we want. We chose 3 different additional shapes. One, this triangular shape here, so that's a simple, just going from a cylindrical to a triangular shaped channel. And number 3 is a snake's tongue, which is essentially kind of a peace sign cooling channel and an additional cooling channel in the midsection of the fuel element. So these are tiny cooling channels. And then what we call the wishbone cooling channel, which is just removing that additional internal channel and lengthening out the legs of that a Y-shaped channel. Okay, so what you see here is you can do this optimization. You do increase pressure drop across the fuel element a bit, not a great deal. But what we're really looking at here is reducing the parameter that we call in-plane delta T. So that's what's really driving the thermomechanical behavior of these designs. And so the wishbone design here that we came up with seems to provide a good combination between low in-plane delta T complexity and relatively low pressure drop. So we take that design and we do additional design optimization, come up with what we call an optimized wishbone design. So this is kind of I'd have to ask another staff member whether it's supervised or unsupervised design optimization. I'm not for sure what they did here, but this is where we ended up in terms of the design space. This is what TCR currently looks like. I know I'm missing some questions. I'm going to try to get through all this, and then I'll try to get to the questions as we start to finish up. Okay, so we did some additional scoping on the wishbone channels. Basically adding in different sections of silicon carbide holding material. Essentially, you can do a lot more here in reducing the in-plane delta T if you add additional silicon carbide in places that you don't want fuel. But of course, then you're also displacing fuel and having an impact on reactivity. So when we evaluate some of these in neutronics, we end up reducing the amount of fuel that we have and reducing the excess reactivity to a point that we don't really want as well. Okay, so this next example, so that was fuel element optimization. The next example is core inlet and outlet optimization. So on the right-hand side there, you see kind of very simplistic layout of the core. The actual vessel doesn't have flat bottom and top. This is just an initial iteration that we used for some FD design scoping. So you'll see this cold inlet here at the bottom. These were just straight inlet channels that flow into this kind of angled section, which is the outlet. Flow then moves around the outside of the reactor, comes up to the top of the reactor, swirls around a bit, and then goes down through the reactor. So both the inlet and the outlet are at the bottom. Cold inlet, cold gas is going around the outside of the core between the fuel and the vessel, and then coming down through the fuel. And so what we were seeing here is with this initial design, we were seeing very, very large pressure drop in the bottom inlet section. So we said, well, let's see what we can do in terms of additive manufacturing to build a better, essentially guide for fluid to flow through to get to cylindrical inlet shape to that annulus shape that goes around the outside of the core. So here you're seeing 3 different design iterations where you essentially have a short section. Here inlet V1 is a short section, V2 is same thing but taller, V3 has some kind of guiding vanes on the inside of that element, and V3 is essentially tilted and the inlets are shaped at a certain angle. Okay, so we did a number of design iterations here, and we printed not full-size versions of these, but we printed some small versions of these to make sure that they would be able to print. We actually do have printers at the MDF that would be big enough to print one of these sections as well. So we felt confident moving forward with potentially taking a look at these for our actual design. Okay, so we did quite a bit of design optimization on the V3 design. Which is essentially this design here, has, the inlets are angled both in X and Y and in the Z directions to a certain angle. And so this best design band shows you, you can't really see the axes here because it's so small, but it shows you the best angles that you can choose for those particular orientations of the inlet. Okay, so here's where we were initially. This is the initial inlet. On the left-hand side, you have this huge pressure drop where you have the inlet gas impinging on that outlet funnel. And then when we move to the V3 design, you can see much, much lower pressure drop or pressure loss in this inlet section. So let's look at some results of the numerous designs that we took a look at. So all the way on the left is the baseline design. This is a pressure loss of about 0.8 psi. Now 0.8 psi doesn't seem like a lot. However, this system is cooled by helium, and the heat exchanger, helium to air heat exchanger, is a significant pressure drop in the system. And optimizing and reducing the pressure losses wherever you can gets you into a place where you can just use one circulator rather than two circulators. So obviously we try to, because we're trying to deploy a system on a short timeline and low cost, we try to eliminate all components that aren't really needed. So we're trying to essentially stay away from having two circulators, and doing these sorts of optimizations were important to essentially gain us the confidence that we could do that. Okay, so the baseline design is a pressure loss of about 0.8 through the bottom of the system. The green that you see there is a flow reversal from Z. So we have flow normally flowing upward. That's where we want it to go. When it's flowing downward, then you see the green in the pictures there. So there's lots of swirling flow in the baseline design. The first iteration of the design, fairly low pressure drop. You know, we reduced the pressure drop by more than half. But we do have some flow reversal that sneaks up kind of halfway up the vessel, which we didn't really want. Version 2, we still had the same kind of pesky flow reversal, even making that section longer. Slightly lower pressure drop, but still flow reversal that we don't want. Version 2.3, which has the vanes on the inside to essentially guide flow inside that kind of complex shaped channel, essentially eliminates all flow reversal inside the vessel portion, but there is some flow reversal within that kind of design itself. V3 that has this tilted angle inlet, you see has almost no flow reversal and has the lowest pressure drop yet. So here's a concrete example where we took our baseline design, knowing that we could additively manufacture this part. We allowed a CFD designer to kind of let his mind run wild and do design optimization and figure out what the most optimized layout would be, which is something like what you would see on the right, where we reduce pressure drop by a factor of 4. And eliminate that flow reversal that we were seeing in the vessel itself. Okay, the next thing I want to talk about is additive manufacturing in terms of the coolant exit of the reactor. So normally reactors have straight vertical channels, and the exit in this particular baseline design, we had this funnel-shaped outlet. What you know in reactor design, you know that in each of these channels there's going to be a different amount of power created. There's more power on the channels in the central portion of the core than there is on the outside portions of the core. So the gas coming out of those central portions are going to be hotter than the gas coming out of the outside. Well, what we want to do is we want to be able to accurately measure the outlet temperature. And as it turns out, where you put a sensor in the outlet has a large impact on the temperature that you measure. So what we did here is what we tried to do is think of ways to essentially change the outlet flow characteristics so that we have some amount of mixing while keeping the pressure low, and get to a point where no matter where we were in the instrumentation plane, we have a reasonable flat temperature distribution across that plane, so we know we're actually measuring the true average outlet temperature. Okay, So essentially what we wanted to do is pursue outlet flow nozzles and optimize the plenum shape. So look at both of those things to reduce pressure loss and reduce in-plane delta T. So this is the straight channels, and the plot on the right and the numbers here on the bottom are really what I want you to look at. The standard deviation of the temperature on the instrument plane is 10.6 degrees Celsius. This is straight channels and this simple baseline design. Really, that's not too bad, but we think we can do a little bit better than that. Okay, so this is just shaping the inlet. Now we don't have a simple cone design. Now we have this more complex shaped inlet. And now we see you can really reduce the standard deviation of the temperature that you see at the instrument plane from 10 down to 1 degree Celsius. And this qualifies, there's not an increase of more than 0.5 psi pressure drop here. Okay, so that's kind of where we ended up. This is including both this outlet design, and we also did tilting of these channels to essentially make the flow swirl and mix without significant pressure loss. So this would include additive manufacturing of these outlets to the coolant outlets into this plenum, and then shaping that plenum in a certain way. Combining those two effects really provided a good benefit. So the other thing I'd like to talk about is, we've talked a lot about additive manufacture. We also have these new advanced characterization techniques that we can use to essentially analyze what we're constructing. So this is a TRISO fuel element. This is actual data that we took using X-ray CT. The data, we can then calculate the actual particle location for every TRISO particle in the system, and then we can put that back into a model. And so here's a video of what those TRISO particles look like. Hopefully the video works without too much issue. Kind of spin slowly. The different colors you see are what X-ray CT thinks that the particle size is. So it thinks that there's a distribution of size of particles there, although X-ray CT probably isn't providing us enough detail to actually characterize the size of the TRISO particles, because the difference in the size of the TRISO particles, the X-ray CT characterized is bigger than we know from traditional characterization. So what we're really using this for is to understand how the particles pack in this fuel element. So in traditional TRISO fuel, you can get to a packing density of 30 or 40%, and that's because you have to compact the fuel. Here we're getting up to TRISO packing fractions of on the order of high 50s to low 60% packing fraction. And that's because we don't have to compact the TRISO particles together with a matrix. We fill the matrix in and then use this chemical vapor infiltration process. Okay, so we want to know what the particle packing characteristics look like from this new type of fuel form and its impacts on thermomechanics. So what you actually see here, I've plotted on the left in XY the center position of all the particles, and then in XZ as well, the center position of all the particles. And what you see here is that along the vertical surfaces, you actually have more dense packing, more ordered packing than you would traditionally expect. So you have along the vertical surfaces, you have packing fractions that are greater than 60%, those that approach random close packing, which is about 65%. And then at the bottom of the fuel element, you also have one very solid, dense layer of particles as well. So if you look at those pictures on the right, you can visually see how the particles are packing in there with one another. This is an older fuel element design, just a simple hexagon with a coolant channel in it, but the particle packing characteristics remain the same. So you can see its impacts on power distribution as well. The top right is a detailed Monte Carlo calculation that was run using these actual particle locations, and you can see you get higher power peaking along the vertical surfaces of the fuel element. We also took those particle locations and built a Bison thermomechanical model to understand how this impacts performance of the fuel element cells. So just two cases we're looking at here. The left case is uniform heat generation, which you would assume might be the case. So if you have uniform heat generation across the entire element, you can see that the temperature peaks in the center. That's farthest from the coolant channels, and then the stress peaks kind of along these points of the elements and along the middle portion of the flats of the elements, which is somewhat expected. So the maximum stress in the fuel element at this using this uniform heat generation rate is about 73, 74 MPa. Okay, so now when we use the actual particle locations, what we see is a reduction in the maximum stress in the fuel element from about 74 MPa to about 53 MPa. And so the question is, why does that happen, right? So if we go back to the last slide, particle packing aligns along the vertical surfaces, and so that's where the coolant is located, right? So you're moving fuel closer to coolant, so you actually have a better optimized layout of fuel and coolant than you otherwise would, and this is just due to the characteristics of the fuel element. Now we do have the maximum stress here still at that bottom portion, right? So we don't have cooling at the bottom and top of the fuel element. That bottom portion, we have very, very dense packing, but no cooling flowing along the bottom. So we do get a stress peak at the bottom of the fuel element. Now, the next step that we're working on right now is adding additively manufactured features to the bottom of the fuel element to essentially disrupt this bottom layer of packing. And we think we can get down to even lower stresses than this by using these additively manufactured features in the fuel element. So this is something that we would never know about unless we had advanced characterization, and we would never be able to fix unless we didn't have additive manufacturing. So quickly, I realize I'm running out of time here. I want to leave some time for questions. We are working significantly on what we call the digital platform. And this really spans all portions, all thrusts of TCR, and I'll get into essentially what we're doing here. This is really in-situ monitoring of the additive manufacturing processes. So on the left, we have to instrument the actual additive manufacturing machine. So we put high-speed cameras, both visual and infrared cameras, on these machines, and we're essentially taking pictures continuously as all parts are being built. So we do data acquisition there. So all of that data goes into a data collection database, I guess you would say. I'm trying to find a better word for it. And then we can start to do machine learning, computer vision type analysis on this data that we have from how the part is being built. From that data, we can start to detect anomalies. So what you're seeing here, the real-time results on the right, I'll play the video again, in green is X-ray CT of these cylinders showing porosity in the 3D printed material. On the right is showing what we expect to see, what we essentially got from our AI machine learning algorithms. You can see that those defects, the AI is capable of picking those defects and telling us where those are. The question then is, are those defects big enough to cause problems in the part? And do you need to post-analyze the part using X-ray CT or other testing means? Eventually, we hope that the answer is no, but right now it is still yes. So TCR, there's a lot of complexity and a lot of work to be done in being able to detect and characterize flaws in these additively manufactured parts. In 2020, we can essentially fairly easily detect a number of defects in the part. In 2020, in TCR, we were able to visualize those defects, which you saw in the last slide. As part of the TCR program, we hope to eventually be predictive, i.e., predict when a part might fail due to those flaws. That requires testing and breaking lots of things that have been additively manufactured. And then further on down the line, we hope to use this to use these machine learning and AI-driven design techniques to essentially make design modifications based on what we're seeing when we're actually printing a part. Okay, so that's the end of the content of the talk. There's some conclusions here. The high-level conclusion is that TCR is doing a lot, not just in additive manufacturing, but in materials and computational sciences, to rapidly try to advance and deploy new reactors. We've quickly gone from a number of designs, down selected and selected a particular design, and hope to be able to deploy that system in a relatively short time frame. Now I'll take any questions. We have 5 minutes left here. All right, I got to see how to. The one thing I don't know how to do yet is actually read the questions. There we go. Page 3, what parts are fuel? Can you guys still, you guys can still see my screen, right?
Yes, we can.
All right, so I'll switch back here. Which is this the question about which parts are fuel? I guess I should go. Really, the green sections are fuel here, and the gray is the printed silicon carbide. This blue thing here is a piece of yttrium hydride. All right, the question is, what's the central component at the right of the figure on page 15? I have to remember what's on page 15. Yeah, the central component here is a yttrium hydride filled stainless steel clad rod. So essentially we have yttrium hydride moderating slugs inside a stainless steel sheath. There's a bottom and top cap that are welded on there, and there's a spring mechanism here to hold all these fuel elements in place. So once you assemble one of these, you have one long fuel element that has been stacked up of multiple components. What other questions here? Yeah, the industrial application really probably would be a high temperature gas cooled reactor. That's certainly what we're shooting for as part of this program. You could potentially use other coolants with these systems and make relatively easy changes. Although we've chosen helium as a coolant just to eliminate complexity with material compatibility and so on and so forth. So several components, several stainless steel components will be printed on different printers, inlets, guides, vessel, so on and so forth, that all welded together afterwards. As a final assembly of the TCR via welding affect the born qualified nature of the individual components before assembly? Yeah, that's a really good question. So one of the things that we're doing as part of the TCR is we have NRC staff that currently are co-located with us to essentially learn what we're doing. So we do have a welding program where we're welding traditionally manufactured parts to stainless steel parts to essentially ensure that those are okay. We'd eventually like to get to the born qualified space, but I think if you're welding components together, you can actually use a similar additive manufactured and monitor the welding process itself to understand what that welding process looks like, similar to an additive process. So there is still some benefit there to essentially have a born qualified component using those welding processes. But it gets to part of the sticky situation that, in nuclear, we are putting multiple components together, and being born qualified would also include irradiation damage and things like that, which still need to be fully assessed. So what are you planning to do with the reactor after operating for 1 day? Could you qualify it to go to higher burnups? So that is certainly something that we've talked about. I think it could, there's enough fuel in the system. Our simulations say that at least in this particular design, we could probably go to 1.5 to 2 years of full operation with the amount of excess reactivity that we can get out of 250 kilograms of HALEU. The reason not to go that far is that there are limits in the system where, when I say system, what I really mean is containment system. So if you have a release of radionuclides, having a low source term really benefits you a lot. So that's part of what drives a 1 day operation. 1 day is a nice round number. It may be 1, it may be 3, it may be a week, but we don't expect to operate this for a very long period of time. Right now, the plan is to take the fuel to a repository and other components to be recycled as they could be. Obviously, everything is going to be activated after it's been operated with neutrons hitting it. So there's only so much that you could recycle, but we think there are some things that could be salvaged from it. We've looked at salvaging the HALEU, although of course once you put HALEU, any uranium, into a TRISO fuel form, it's extremely hard to get out. So it would be essentially having to grind up the fuel and then dissolve it, which is complex and probably really beyond the scope of what we want to do with the TCR program. So what's the process for converting complex CAD geometries to reactor physics models? There is a process to do some of that, although it's very, it's not great. So what we do now is essentially, we're still modeling most things using MCMP or Kino type combinatorial geometry and not using the actual CAD geometry in terms of the neutronic calculations. Luckily in this system, in terms of neutronics, the system is not that sensitive to these very small changes or simplifications that we make in the geometry in order to be able to model it. So we do actually model the physical overall shape of the fuel element. We're not modeling any complex cooling channels or anything like that. As far as CAD modeling for MCMP and Shift, we have a lot of people working on that at Oak Ridge, and there's always issues. I have not tried to convert the TCR geometry myself. We have colleagues at Argonne National Lab that have been working on converting the TCR geometry to CAD, from CAD to be able to run in Serpent. And what they ended up doing was using CAD everywhere else other than the in-core components, because there's a number of things that need to be kind of cleaned up in the CAD models before we can really do a full conversion there. Could these elements eventually be used in a commercial reactor? I think the answer to that is yes. Of course, all these components have to be qualified under irradiation, which we're pursuing right now. We're doing fuel irradiation at the MIT research reactor, and we're also doing fuel irradiation in the fuel testing in the Idaho treat reactor as well. So we're working on all that, but it's not all there yet. I think with that, I'm probably about out of time. A couple minutes over. If anybody has any burning questions, I'd be happy to answer it again. Or you can email me. My Oak Ridge National Lab profile page is easy to find. Just Google my name and ORNL, and you'll find me and my email and be able to contact me.
Thank you very much for your talk, Brian. That was extremely interesting, and it's really amazing that you're able to build something and get it to the point of operation within such a short time and introduce all these really interesting new technologies. So it's been really fascinating. Thank you.
Thanks a lot. You guys have a